So welcome to Dr. Carl Society Mission. We want to start with an interesting topic, but let me first welcome you to physics. Okay, so this is physics. Okay, now physics for kids and adults together. So for the kids, we are looking at 6 minutes. The lowest we are going for will be 6 years to 8 years as the minimum. Okay, so we'll be teaching up to that level, and then for the upper primary and then JHS, SHS, university, postgraduate will go to that level depending on how the topics are. So let's all join as we continue with physics. We've already finished with maths. I always say that the chapter 1 of physics is mathematics. So since we finished chapter 1 of physics, that is mathematics, we are now going to look at physics itself. So physics, right? Now, what is physics? Because usually it's concerned with the physical properties, the things that we can use our senses to detect. Okay, we have 5 senses, things that we can use our senses to detect. Okay, right? At least, or use other means to detect their presence physically. Okay, then all those things will fall under. How they work and function and interact will fall under physics. So under physics, the major parts, the major thing that we'll be studying or be talking about will be motion, energy, and then forces, right? So let's continue. So the first thing I want to know, since we are dealing with kids as well, usually we'll start from the kids level and then move up. Okay, so for kids, the force with you. Okay, so when you're talking about force, we are looking at how you can pull something, how you can push, how you can twist something. Okay, what helps you to do that? Now there's a special force that enables things to rotate or turn. Okay, turning force. I would refer to that one as the torque. Okay, and it's very important when it comes to turning. Okay, that becomes the effective force. But for non-rotating objects, okay, then the linear form of force and other things will come to play. Right, so that is that. Now let's go about motion. That's something changing its position. Okay, right. Now we can look at it as a speed and direction. Speed and direction, then talking about velocity. Okay, right. So the speed, if we have another dimension added, then it's velocity, right? So somebody will call it the invisible superpower. The invisible superpower, that is the gravity. So when an apple falls, according to Newton, why doesn't the apple fall or go into the sky but falls down? Okay, something pulls it, and this is universal occurrence. Okay, right. So kinetic energy, right. So we will look at the energy, that's the power to do things. Okay, the power to do things. Okay, right. So energy allows things to happen. So we have kinetic energy, that is energy of motion. Potential energy, that is stored up energy by virtue of your position or the molecules in the molecules, their reference positions. Okay. Simple machines. Okay, we have the first class, second class, third class. PLE, pivot in the middle, load in the middle, effort in the middle. These are classifications of simple machines. Okay, coming down to the level. So these are sometimes what machines, of course, or the levers are. What they are doing is they are seeking to leverage. Okay, seeking to make you use a smaller form of something to be able to achieve a bigger output. Okay, right. So maybe the mechanical distance allows you to be able to push something bigger. Okay, so these are ways that the pulleys are also there. Okay, so we can look at all this. So some of these simple machines, you have the levers, we have the pulleys, we have the wheels, we have the rams, so on and so forth. Now, so the simple machines, like we said, the levers, the pulleys, the wheels, the rams, is okay. So now the first thing that we're going to do, we're going to talk about dynamics or motion. Right. So we'll first look at the 4-5 equations of motion. The first equation of motion is V is equal to U plus AT, and this is derived as of course when we have the distance or this displacement. Okay, you're looking at your velocity times your time. Now usually we usually look at two velocities. Okay, so from one to the next, the distance you've occupied is always to look at the formulas in that way. So from one to the next, the distance you've occupied. So if we want, since we have the beginning and the end, if it is smooth travel from one end to the end to the other, okay, then integration can be applied, or you can just sum the first and then the second, especially where the graduation is predictable and smooth, okay, and then in the same constant increase, all right. So the same constant value increase, okay. So in that sense, you can just look at the first and second. So your average distance, your average velocity times time will give you the displacement, right? So that will be U plus V over 2 times T gives you, and then from this we can get a lot of equations, right? Now we look at the first equation with reference to acceleration. So acceleration 2 is the rate of change of what velocity. So how velocity is changing from one velocity to the next velocity over time, and that is what we have as our first equation here, rewritten as this, right? Okay, so acceleration is this final minus initial over t, and that is acceleration. So this is about all these equations that we're talking about are equations, linear equation, linear motion, okay, equations. So we go. Now let's look at the second equation. That's ut plus half ats, okay, at to the power squared, okay. Now this acceleration, due to acceleration, it can be, if it is something under gravity, then the acceleration a becomes g, and because it is always pointing downwards, it will become negative g, right? Okay, so there is a second equation, note it, that is also derived. If you have the first equation, displacement is equal to u plus v over 2 times t, and you substitute the acceleration in. Of course, you may arrive at this equation. So there is it. Okay, so first we have this is using the graph method to derive it. Okay, but like I said, if we had some of the ways to derive, you have displacement is equal to velocity, final velocity plus initial velocity divided by 2 times t. Now we already know acceleration is equal to v, final velocity minus u over t. All right, so we can substitute this one, okay, or if we decide to multiply through by t, the first equation s is equal to v plus u over 2, but if you multiply if we divide through by t, let's see, we're going to get 2s v plus u times t. Now divide through by t, right? So that will give us 2 times velocity is equal to acceleration plus t, right? So you can do the manipulations, you substitute for the other depending on what values you want to get into the equation. So here, this the second equation, let me go back and get it well for you. We want to have an expression with g, acceleration with acceleration, and then u, okay. So acceleration and the u, so it means our equation s is equal to v plus u over 2e. We can replace the v by an expression that has a in it. Already know a is equal to v minus u over t, so we can make v is equal to AT plus U. Right, so if we put that in, S is equal to V plus U over 2, we're going to get AT plus U over 2 times T. Okay, and this is going to give us here, if you split it, we're going to have our ut over 2 a over 2 times t is equal to s. Right, so if we allow this one to move just like we did, so let me just get it here so that it becomes easier. Okay, so we have s is equal to v plus u over 2 times t, but we know v is equal to at plus u times t. Okay, right, so if we multiply through, we're going to get at squared over 2 plus ut over 2. Okay, if we multiply through by 2, right, so we have our ut squared here. Okay, so that will be our 2 comes out, and then we will have the final expression as this one. Okay, like we have here. Right, so let's see how this one also got it. Now they use the triangles. Okay, right, so we have our ut, so this is u times this as ut. Okay, and then triangle here is giving us remember this is half t, and this is what we are having here. Right, now this is also equal to this. Substitute this into the equation. So the triangle, substitute it, we're going to have this. Okay, so the total displacement, we are ut, and then the next area added. Okay, now let's look at the next equation. So here we want to have v and u without t, so it means we substitute, we find an expression for t and substitute for t in that equation, and you'll be able to get rid of all the others and then have this. So usually you do this by just examining the equation, see the variables you want, and then substitute for the other ones. Okay, so that is it. Now there's something here, let me go through let's go to the fourth one. After that we will just go over again so that you have, so that's the last equation, the third equation that we have here. That's it. Okay, now so let me just go over for the sake of reinforcement. Right, so we said the first equation, we have acceleration, which is given by, acceleration is what? Your velocity, final velocity minus your initial velocity over time. That's one equation. Now we know this displacement is also equal to the average velocity times time. So average is v, final velocity v, and u divided by 2 times t. Right, so these are the two equations that we'll be using. Okay, so the next thing is we want this equation, the second equation. Right, let me go to the second equation. We want an equation which has s, which has u, and which has t and a. Right, so if we take our second equation where s is equal to v plus u over 2 equal to t, we can have that. We can try our hands on that one. Okay, so in that sense, we want to have SUTA. Okay, so we don't have a in the second equation, which is the displacement equation. So what we can do is we can substitute this one, equation 1, where the expression for acceleration is given. Okay, so we have acceleration that will give us at is equal to v minus u. This v, for this we can have v is equal to u plus at. Now if we substitute that one, s is equal to u plus at plus u, all this over 2 times t. Right. So if we do that, what we're going to get is we're going to get u 2u plus at squared all over 2. So s then will be equal to the 2 will cancel the 2u, so we have u, so ut. Let me add my t here. T here, so we have ut plus half at squared. So that gives us the third equation. Now for the fourth equation, it's an equation that we don't want t to be in, so we can substitute for t. Okay, so we look for, from the same equation, acceleration is equal to v minus u over t. Make t the subject, so t will be equal to v minus u over a. So if you substitute for t in the same equation where displacement is equal to average velocity times time, so we put that one there. We're going to get s is equal to v plus u over 2 times t. The t is now v minus u over a. Now this is what is going to happen. We're going to get s is equal to, okay, so we have to multiply. V times v will give us v squared. Okay, v times u will be vu. U times v will be plus uv, and then u times u will be minus u squared. All this over 2a. Right. So our uv will cancel out. So we have s is equal to v squared is equal to, minus u squared over 2a. Now this a can cross, so that we have 2as is equal to v squared minus us, and therefore v squared will be equal to u squared plus 2as. That's the final equation. So these ones are relatively easy to derive. So you first have to start with your acceleration, and then you have your other expression, which is the displacement is equal to average velocity times time. The average velocity will be final velocity plus initial velocity divided by 2. Then you get that. Right, so that is it. Now we move. Third equation, I've already talked about that. Okay, so we have these expressions, we talk about them. So we can look at work examples. These ones have been derived for us. Okay, so that's looking at where it starts from, and then it goes in that order. Now there is another thing we have to look at as well. And this is the relative velocity. So we are looking at relative velocity. So if you want to get the velocity of one object relative to the other one, okay, so what you do is the one that you want to get its velocity. So relative velocity of a with respect to, let's say, b, then it means the velocity of a as seen by b. Okay, so the reference point 1 is the one you subtract. Okay, you subtract the reference 1 from the one you want to determine the velocity. Okay, so relative velocity of a, okay, or velocity of a as seen by b. Okay, so the velocity of a as seen by b, so we will assume b is moving and a is the reference one, so it's not moving. So you subtract a's velocity from the one that is moving. But remember, you have to choose a direction. So if once you make a direction, the one going against the direction will have a negative velocity, and one going in the direction will have a positive velocity. Right. Now let's also look at the next thing, which is very important and crucial, which is the coefficient of restitution. So this one, we are interested in two bodies colliding. We want to see the energy they had, and then after colliding, how much energy they have. Okay, so this is just to help us to know whether the collision is elastic or inelastic. So if it is elastic, then when they hit each other, they move apart, okay, with the same velocity, so no energy is lost. Okay, now the inelastic, when they hit each other, they may stick together. Friction and other things may consume part of the energy, right? So that is that. So your final velocity, the sum of your, the relative velocity. Let's go to. I want us to look at restitution, coefficient of the restitution coefficient. That one didn't come out here. But we'll look at that. Okay. So once you're looking at the restitution, you look at the final velocities. Okay, the difference as against the initial velocities. Okay, you compare to see. Okay, to determine whether it's elastic or inelastic. Right. Now let's go to the next one. Displacement. For displacement, you use the graph. Okay, so y positive, y negative, x positive, x negative, and in that order. Then velocity will follow the displacement. When it is coming down, the final velocity is in the same, is bigger than the final velocity, that is when it is coming down, the final velocity as against the initial velocity. So you have a negative sign as the velocity is coming down. Now the other thing that we need to look at is if you are going against, acceleration due to gravity is given negative. So if you are going against it, then it's positive. So the upward movement of velocity is positive. When it is coming down, it's negative. But gravity is always pointing downwards, so it's negative. So that one, you maintain the negative sign in the equation. Right. So I think this is all that this is seeking to do. So we'll then look at the projectile equations. Okay. So for the projectile, the same 4 equations that we have for linear, you use that for the projectile. Okay, so for projectile, we have the initial velocity. If it is thrown at an angle, it will have its vertical component, and then have its horizontal component. The horizontal will not have any position unless we say there's air resistance, and then the vertical will go against gravity. Okay, right? So that will make it reducing its speed as it moves upwards. Okay, so that's crucial for us to note that. Okay, now we can then resolve the various velocities in x and y direction to calculate for horizontal distance, the vertical distance, and other questions with respect to time. Right. So now, what is a vector? A vector will have both magnitude and direction. Already talked about this, so I won't do it. So we can add vectors, subtract vectors based on their locations. Okay. So if it's y, add x, y and y, x and x, in that order to get your this. Right. Now, something more. We talk about projectile already, horizontal motion. So the horizontal motion is u is equal to u cos theta. It's always so. The vertical motion is u sin theta. So cos is usually for the horizontal, so that is what is going to be mentioned here. All right. Now this is equation similar to the projectile, okay, but it's starting at a height above the ground. So we put y0, that's the initial height, and then we add our equations here as it's moving upwards. Okay, equation, right? So I have the work examples, North Pole. So if you also want to calculate the magnitude and bearing, okay, when you have the coordinates, the x part can be squared, the y part can be squared, and then the hypotenuse is the actual thing. Okay, so we can use Pythagoras theorem to get the length of the of any 2 points linked by a line, right? So we show some sketches, okay? The sum of angles, right? So that's it. If you note it, 180 angles on a straight line is 180. You can divide it several times. They should all add up to 180, right? So we have the scalar quantities which do not have direction, and then we have the vector quantities, okay? Right, so the fundamental dimensional units, mass, length, time, okay? You can use that one to derive formulas, okay? So this is what we are doing here. So once we know the unit for the quantity, we put them in the decimal, and then when we rearrange and do them well, we'll be able to determine determine what is left in the equation. We have classical physics here. Other types of physics may exist. Okay. So special relativity, that is with respect to light. This into travel up and down. Time t is given by this, where c is the speed of light. So not this one. The moving object, and so on and so forth. The word theorem is used, yeah, same thing. Derivation of length contraction, okay. So that is. So we also have a relativistic mass. Okay, so when you're at rest and then when you are moving, okay. So at rest is MO, and this. So this is a mass and relativistic mass given by the formula, right? So the big idea, speed and time. As you move close to the speed of light, everything in the time frame of movement will start slowing down. Okay, its relative will start slowing down. So by the time you return to Earth, your mates are already gone and you are still not old. Right, so the paradox of time, talk about that. So photon by Einstein, okay, hits a metal, ejects electrons, photoelectric effect. Okay, so we have the equations. Photon energy. So photon kinetics. So we have this, and then we have that rest mass and then mass in motion. Okay. Now let's look at the discovery of the subatomic particles. So electron by J.G. Nucleon, okay, by other factors and so on. So this is the Rutherford Goldford experiment. To Newton. So we look at energy, greater energy, kinetic energy, and so on. Right. The Bose model is there. So mass energy conversion, rest mass. Okay. Remember the contraction in mass also account for energy. So momentum conservation. I think I'll leave it here, but we'll look at it. Momentum conservation. Right, so momentum is conserved in many instances. Okay.